Many people think of math as a dry, frustrating, or scary subject. For these people, doing math is like crossing a desert, or trying to escape from a straitjacket, or hanging on to the edge of a cliff for dear life. Because so many people fear or dislike math, teachers sometimes try and hide the math or sweep the math under the rug when they teach.
Just a minute. Okay. You can come in now.
Teachers typically try to make math more palatable or less scary in two ways. They teach the math using engaging or authentic real-world applications, or they personalize the math to try and match each student's individual interests or their thoughts on their preferred way of learning. While these approaches seem helpful, research shows that they can actually interfere with how our brain naturally builds mathematical understanding. Let's start with teaching through real-world applications. Both Barb and I believe that teachers should show students the relevance, power, and beauty of math by teaching them how to solve interesting real-world problems. But real-world problems can be complex, and some problems can only be described using text or language that is challenging for students. If teachers start with problems that are too complex, that push students out of the 85% zone, students start to struggle and can quickly develop a fear or dislike of math. Basically, over-complex problems can overwhelm students' working memory before they've had a chance to build strong mental schemas, those frameworks that combine both conscious understanding and automatic pattern recognition. But there's an even more fundamental issue here. When students learn primarily through concrete examples, like counting pizza slices or using measuring cups, they often struggle to see past those specific contexts to grasp the core mathematical concepts. It's not just that the real-world details are distracting. Research shows they can actually bind mathematical thinking to particular scenarios, making it harder for students to recognize and apply the same concepts in new situations. And there's a related drawback to real-world applications. Students are more likely to transfer knowledge, which means applying the concept to a new situation, if they learn the concept from an abstract or generic representation than if they learn the concept from multiple concrete or real-world examples or representations. Here's what the research tells us, and it connects directly to what we learned about schemas. When students get stuck in concrete details, they can't develop those powerful mental shortcuts that experts use. Remember how physics grad students could look past whether a problem had springs or ramps and see the deeper patterns? The same thing happens in math. When we strip away all the extra details, both learning systems can work together effectively. The hippocampus can process the core concepts, while the basal ganglia can build automatic recognition patterns. This teamwork is what leads to true mastery.
When we strip away the extra details, students can develop rich schemas that include both types of understanding: the conscious grasp of concepts through the hippocampus and the automatic recognition of patterns through the basal ganglia. This integration is what leads to true mathematical expertise. The researchers found that while concrete examples sometimes helped with initial learning, they consistently interfered with building complete schemas that could transfer to new situations. Students who learned through abstract representations were better able to develop schemas with both strong declarative understanding and automatic pattern recognition. In fact, research suggests we might want to flip our typical approach. Rather than starting with concrete examples and trying to move towards abstraction, beginning with simple abstract representations helps students focus on the essential mathematical relationships. Then, once they grasp those core patterns, we can show how they appear in real-world contexts.
It can help to take a closer look at research by psychologist Jennifer Kaminsky and colleagues. In one study, the researchers asked teachers whether students would be more likely to develop proficiency in reading bar graphs if they were taught with the kinds of bar graphs shown on the left or the kinds on the right. Most teachers picked the graphs with pictures in the bars. The ones on the left, because they said the pictures were concrete representations of the problem and were more visually appealing and engaging. But in the study, students learned better from the generic black and gray graphs on the right. Bar graph C on the left is particularly confusing because the number of objects doesn't match the scale. In another study, Kaminsky's group also found that students learn fraction concepts better from more abstract representations, like the ones you see here on the right. In both studies, the extraneous information in the representations distracted students and made it harder for them to see the deeper mathematical structure in each scenario. Thankfully, these structures, which underlie an astonishing variety of real-world math applications, are usually simple and accessible to any brain. When we strip away the extra details, our basal ganglia can do what it does best: start recognizing patterns automatically. The researchers found that while concrete examples sometimes helped with initial learning, they consistently hurt students' ability to transfer knowledge to new contexts. Students who learned through abstract representations were much better able to recognize and apply those mathematical patterns in new situations.
Now, I know what some of you might be thinking, but my students love it when I bring in real-world examples. Won't math be boring without them?
That's exactly the challenge we want to tackle next. Barb and I both believe that students enjoy applying math in the real world, but making math engaging isn't necessarily about dressing it up in real-world clothes. It's about helping students experience those aha moments when they grasp a powerful mathematical idea.
And what's really cool is that when students start spotting those underlying patterns, when they build those mental schemas we talked about earlier, they actually get more interested in math, not less. They start seeing connections everywhere.
In our next video, we'll show you how to create lessons that capture students' interest while keeping the mathematical ideas crystal clear. You'll see how starting with simpler, more abstract representations can actually lead to deeper engagement, and yes, even excitement about math.